One of the original reasons for developing the calculus, and in particular the notion of derivative, was to understand gravitational force. For a body falling in a vacuum, the first stage was to experimentally determine the formula for the distance fallen as a function of time, call it s of t. The next stage was to realize that if you know s of t, then you know the instantaneous velocity at any time, namely v of t equals s prime of t. However, to understand gravitation, it is necessary to understand Newton's amazing law F equals ma. That is, the gravitational force, or any other force, can be determined if you know the mass and the acceleration of the body. It was just a small step to realize that the acceleration a of t is the derivative of the velocity v of t. So for example, if we know that s of t, the distance that the object has fallen, is given by the formula 3t plus 4.9 times t squared meters with time in seconds, then v of t will be the derivative, 3 plus 9.8 t meters per second. And a of t, the acceleration, is 9.8 meters per second squared. The point is that to get the acceleration, we have to differentiate the distance function twice. This is called the second derivative of s of t and is written in several different ways. S with two primes, or d squared s dt squared, or capital D with a superscript 2 of s in brackets of t. As we shall see throughout our course, the higher derivatives are all important. That is, there's no reason to stop with the second derivative. In our example, the third derivative of s of t is just the derivative of s double. That is, s triple prime of t is the derivative of s double prime of t, which is the derivative of the constant 9.8, which is 0. Putting so many primes after a symbol is a nuisance, so for higher derivatives, we often write s with a superscript 3 in parentheses of t rather than s triple prime. Notice the parentheses around the 3 to show it is not a power, but a third derivative. Here's an example of higher derivatives for a given function. If f of x equals 3x to the 6th, then f prime at x is 18x to the 5th. F double prime of x is 90x to the 4th. The third derivative of x is the derivative of f double prime, which is 360x cubed. The fourth derivative is 1080 times x squared. The fifth derivative is 2160 times x. And the sixth derivative is 2160. The seventh derivative is, of course, 0, and so will all subsequent derivatives. In fact, this always happens with a polynomial. Eventually, you get a higher derivative that is 0. For a polynomial of degree n, it will be the n plus first derivative. Here's an example with a trig function. G of x is sine x. G prime of x is cos x. G double prime of x is minus the sine of x. The third derivative is minus the cosine of x. The fourth derivative is the sine of x, which is just the original function g of x. Since the fourth derivative is the original function, we know the successive higher derivatives will just cycle through those first four. The fifth derivative, for example, is the derivative of g4, which is the same as g prime, which is cos x, and so on. We can immediately conclude, for example, that the ninth derivative of this function is the same as the fifth derivative, which is cos x. For more complicated functions, the computation of higher derivatives can be a frustrating exercise in using the various rules for derivatives. Consider the function f of x equals e to the sine x. The first derivative isn't too bad. That's just cos x e to the sine x using the chain rule. But now you have to use, for the second derivative, the product rule combined with the chain rule on the exponential. So you get minus the sine of x times e to the sine x plus cos squared x times e to the sine x. Still not too bad because you can factor out e to the sine x and your coefficient is minus sine x plus cos squared. Now you have to use the product rule on that expression to get the third derivative. And I won't even spell it out in words. You can look at it on the screen. Each successive higher derivative is got by differentiating the previous higher derivative, and they do get messy for this function. This is where Maple and Mathematica, the two competing computer-based mathematics software programs, come into play. All I have to do is type in the appropriate command, and either one of these systems will immediately give me the fourth derivative of e to the sine x, which I have written out here and which I'm definitely not going to read out.